At the smallest scales of the universe, far below anything that can be seen or touched, modern experiments have revealed something quietly unsettling, a hidden architecture where pairs of particles behave as though their separation were incomplete. And tonight, we explore how these quantum threads weave the very fabric of reality. Welcome to The Whispering Scientist. If you enjoy drifting through questions like this, you are very welcome to join our slower explorations of the cosmos. As you settle in, let your mind relax and follow the gentle rhythm of the subatomic world. This journey is not one of speed or sharp conclusions, but of gradual understanding. We begin at the very foundation of things, in a domain where our eyes cannot reach, but our logic must follow. Imagine, if you will, the vast emptiness of space, and then imagine zooming in closer and closer, past the molecules of the air, past the atoms themselves, until you reach a layer where the familiar rules of the macroscopic world simply stop applying. Here, in the quiet depth of the quantum realm, nature reveals a feature called entanglement. It is a repeatable feature of the physical world, not a rare anomaly or an error in our machines, but a fundamental truth about how the universe is organized. In our everyday experience, objects are individuals. If you move a cup on your table, the chairs in the room remain unmoved. If you switch on a lamp in one corner, the shadows in the opposite corner change only because light has traveled across the room to meet them. We are used to a world of absolute separation where distance acts as a barrier and influence requires a physical signal or a direct touch. However, the modern study of quantum entanglement suggests that at a fundamental level, nature does not always divide itself along such familiar lines. What appears to be two separate things may actually be a single extended system that refuses to be broken apart. This concept did not arrive as a sudden, loud discovery, but as a quiet consequence of the mathematics used to describe the smallest building blocks of nature. It emerged from the equations that successful physicists have used for over a century to understand the behavior of electrons, photons, and quarks. When we look at these particles, we find that they do not behave like tiny billiard balls bouncing off one another. Instead, they behave like patterns of probability, ripples in a vast ocean of information. Once two particles interact in a specific way, they can become linked in their behavior, sharing a single description that persists even after they are pulled far apart. This link is the invisible thread of our chapter title. It is not a physical knot, nor is it a mysterious force like a rubber band pulling the particles together. It is something deeper and subtler. It is a shared identity. When we measure one of these particles, the outcome we observe is reflected in its partner. This happens not after a delay, not through any detectable signal, but simply as a part of a unified whole. According to our everyday experience, this should be impossible. We expect signals to take time to travel. We expect objects to carry their own properties, fixed and independent wherever they go. Yet, as we refine our tabletop experiments and our international collaborations, the results remain consistent. The connections persist, the correlations hold. This journey into entanglement is not a paradox to be solved with stress or urgency, but a feature to be understood slowly. It is a phenomenon that challenges our intuition without threatening the underlying order of the universe. It suggests that the cosmos is more deeply coordinated than we were prepared to expect. As you listen, let the weight of your day fall away, much like the classical rules fall away when we zoom into the quantum scale. There is a calm beauty in the idea that things are more connected than they seem. For decades, physicists in darkened laboratories across the world have prepared these systems with extreme care, isolating the smallest interactions imaginable to see if this link survives. Time and again, they find that it does. Whether the particles are inches apart or separated by continents, they remain part of a shared history. This shared history is what defines them. Think of it as a story where the characters are so tightly woven together that you cannot describe one without the other. If you change the context of the first, the second responds accordingly, as if they were still standing side by side. We are used to thinking of here and there as absolute categories, but entanglement suggests that here and there can sometimes be the same place in the eyes of the universe. This does not mean the universe is chaotic. In fact, it is the opposite. It is a sign of a very high degree of order and mathematical precision. These quantum experiments ask not for our belief, but for our patience as we rethink what separation really means. Every time we confirm these correlations, we are reminded that our human perspective is just one way of looking at reality. Beneath the surface of our experience, there is a layer of coordination that is silent, robust, and profoundly still. It is a domain where familiar rules stop applying, but where new, more beautiful rules take their place. As we begin to explore these connections, let yourself settle into the stillness. There is no need to grasp the entirety of the theory tonight. It is enough to know that the smallest parts of our world are holding on to one another across the void in a way that science is only just beginning to map with total clarity. This chapter establishes the foundation for everything to follow. It places entanglement firmly within the world of science, moving it away from magic and into the realm of testable, repeatable observation. The difficulty we feel is not because the theory is inaccurate, but because our minds are built for the world of large objects. By placing entanglement in its scientific context, we can approach it without distortion. It is a consequence of how microscopic systems share energy and information. It is an invitation to look deeper. Once this foundation is in place, we can narrow our attention and look at the specific relationships that make this one of the most profound features of the modern scientific view. Nature is whispering its secrets in the language of these correlations. We are here to listen, slowly and carefully. The universe at its most fundamental level is a set of relationships, a vast network of patterns that only settle into outcomes when we look at them. This realization is the first step on a long, quiet path toward understanding the heart of reality. As we move forward, we carry this idea with us, that distance is not always a barrier, and that the universe remembers its connections. It is a grounding thought, one that allows us to feel at home in a cosmos that is much larger and more intricate than we ever imagined. Settle into this quietude, and let the idea of the invisible thread guide you into a deeper, more restful state of curiosity. In the quiet expansion of our understanding, we must eventually confront the barrier that stands between our minds and the quantum world, the steady, reliable experience of everyday life. Our brains have been shaped by millions of years of interaction with a world of large, solid objects, and as we move deeper into the study of entanglement, we find that these evolutionary habits create a profound mismatch with the reality of the subatomic scale. To understand why quantum behavior feels so strange, we must first look at the intuition we are being asked to leave behind. In our daily lives, space is a dominant and absolute master. We understand the world through the lens of local influence, where for one thing to affect another, there must be a physical proximity or a message sent across the gap. If you throw a stone into a still pond, the ripples move outward in a predictable sequential fashion. The water near the center moves first, then the water further out, and finally the reeds at the edge of the pond sway in response. There is a clear chain of cause and effect, and that chain takes time to travel through space. This is the world of classical physics, a world of local realism where objects exist in specific places and carry their own properties regardless of what is happening elsewhere. In this familiar reality, separation is a final and defining characteristic. When you break a piece of bread into two, you now have two independent objects, each with its own weight, its own texture, and its own future. What happens to the crust in your left hand has no immediate physical bearing on the crumb in your right. This sense of independence is the cornerstone of our sanity. It allows us to build houses, navigate oceans, and predict the motion of the planets. It is a logic of parts, where the whole is simply the sum of its independent pieces. However, as we descend into the quantum layer, this logic begins to fade like a dream upon waking. The microscopic building blocks of the universe, the electrons and photons that form the base of everything we see, do not behave like tiny versions of the stones we throw into ponds. They do not possess fixed, definite identities that they carry with them from place to place. Instead, at this fundamental level, nature seems to operate on a principle of relationships rather than isolated attributes. This is the first place where our intuition begins to struggle, as it asks us to imagine a world where the act of separation does not necessarily create independence. In the quantum framework, systems that have interacted with one another can remain part of a shared description, even as the physical distance between them grows to vast proportions. Our intuition tells us that if two particles move a mile apart, they are two things. Quantum mechanics tells us they can still be one thing. This mismatch is not a flaw in our intelligence, but a reflection of the scale at which we live. We are macroscopic beings living in a world of averages. The solid feel of a table or the predictable path of a falling leaf is the result of trillions upon trillions of quantum interactions, averaging out into a stable, classical behavior. Because we only ever see the average, the underlying truth of individual quantum systems feels alien to us. We expect a particle to have a specific location, just as we expect a car to be in a specific parking spot. But in the quantum realm, a particle exists as a cloud of possibilities, a wave of potential that only settles into a single outcome when a measurement is made. When two such particles are entangled, their clouds of possibility are linked. The outcome for one is tethered to the outcome for the other, not because they are talking to each other across the distance, but because they are part of the same mathematical wave. To wrap our minds around this, we must allow our rigid concepts of here and there to soften. In the classical world, here is where I am, and there is where you are, and the space between us is a void that must be crossed. In the quantum world, space does not always act as a divider. Two entangled particles can be separated by the entire width of a galaxy, yet the universe still treats them as a single entry in its ledger of information. This suggests space may not be as fundamental as we once thought. It might be a secondary feature, something that emerges from a deeper web of quantum connections. This realization is unsettling and deeply peaceful. It suggests an underlying coherence to the universe, a hidden layer of unity that remains intact even when things appear to be drifting apart. As you listen, let the frustration of trying to visualize this fade away. You cannot visualize it because your visual brain is a classical tool. Instead, feel the logic of it. Think of it as a harmony in music. Two notes played at the same time are separate sounds, yet they create a single chord that is distinct from either note alone. If you change one note, the chord character changes instantly. The relationship is the reality. Our intuition also struggles with the idea of randomness. We like to believe that if we knew everything about a system, the position of every atom and the strength of every force, we could predict the future with perfect certainty. We view randomness as a lack of information. We think a coin toss is random only because we don't know the exact angle of the thumb or the resistance of the air. But in the quantum world, randomness is a fundamental feature. It is embedded in nature's clockwork. Before a measurement is made, the universe itself has not yet decided on the outcome. Entanglement takes this fundamental randomness and coordinates it. If you have two entangled quantum coins, they will each land on heads or tails at random, but they will always land in a way that matches or opposes their partner. This is the heart of the mystery. Our classical minds want to believe there is a hidden secret inside the coins, a prearranged plan that tells them how to land. Yet, as we will explore in the chapters to come, physics has shown that there is no such plan. The coordination is spontaneous and instantaneous. This mismatch between our experience and the quantum truth is why entanglement was once called spooky. It feels like magic because it violates the local realism we rely on to stay sane and safe in our daily lives. But as we sit here in the quiet of the night, we can begin to appreciate the beauty of this mismatch. It reminds us that we are part of something far more complex and interesting than our eyes lead us to believe. We are like observers looking at the surface of a deep ocean, seeing only the waves and thinking that the waves are the whole story. Entanglement is a glimpse into the deep currents below, where the water is still connected and vast. By acknowledging that our intuition has limits, we open ourselves to a deeper understanding of the cosmos. We learn to trust the evidence of our experiments over our ancestors' habits. We begin to see that separation is a perspective, but connection is a fundamental law. The mismatch is not a barrier to be broken, but a doorway to be walked through, slowly and with a quiet mind. As we prepare to look closer at the discrete nature of the universe itself, to truly understand how two things can become one, in the eyes of nature, we must first descend into the specific way the universe organizes its most basic ingredients, moving away from the idea of a smooth, continuous reality into the realm of the discrete. For most of human history, we imagined that the world was made of substances that could be divided infinitely, like a stream of water that remains water no matter how small the drop. But at the dawn of the 20th century, physicists discovered that if you zoom in far enough, the smoothness of the world begins to break apart into individual, distinct steps. This is the concept of the quantum, a word that simply means a specific, countable amount. Energy, light, and the properties of matter do not exist as a sliding scale, but as fixed packets. Imagine a ramp leading up to a platform. You can stand at any height along that ramp. This is the classical view. Now, imagine a staircase instead. On a staircase, you can stand on the first step or the second, but you cannot exist in the space between them. You are either at one energy level or the next. This discrete nature of reality is the quiet heartbeat of quantum mechanics, and it is the necessary foundation for the shared description that makes entanglement possible. In this granular world, the properties of a particle, such as its position, its momentum, or its spin, are not just smaller versions of the properties we see in a spinning top or a moving car. They are governed by a mathematical structure called wave functions. This wave function is not a physical object you can touch. It is a description of all the possibilities a particle holds within itself. Before we look at a particle, it does not necessarily have a single, fixed state. Instead, it exists in a superposition of many states at once, a gentle cloud of perhaps and maybe. It is only when an interaction occurs, such as a measurement in a laboratory, that these possibilities settle into one definite outcome. When we speak of entanglement, we are talking about what happens when the wave functions of two separate particles overlap and merge. During their interaction, their individual lists of possibilities are traded and combined until they no longer have separate descriptions. They become governed by a single, joint wave function. From that moment on, even if the particles are moved to opposite sides of a laboratory or opposite sides of a solar system, the mathematics of the universe does not see two independent objects. It sees one system described by one set of probabilities. This shared description is the mechanism behind the coordination we observe. Because there is only one wave function for the pair, any action taken upon one part of the system is an action taken upon the whole. Our classical minds struggle with this because we see two distinct points in space. But the underlying information of the universe does not use our coordinate system. In the ledger of nature, the identity of these particles is defined by their relationship to one another rather than their location in the void. This is why, when a physicist measures the spin of one entangled particle and finds it to be up, The other particle's state is immediately known to be down, even if no signal has passed between them. The measurement didn't just change one particle, it resolved the single shared description that covered both. The staircase of their possible states had to be climbed together. To understand this without stress, imagine a pair of gloves that have been separated into two different boxes. In a classical world, the glove in the box is either a left-hand glove or a right-hand glove the moment it is manufactured. But in the quantum world, the gloves are in a state of being both and neither until one box is opened. The moment you see a left-handed glove in the first box, the other glove, regardless of where it is, must be the right-handed one. They share a single description of a pair, and that description remains valid no matter how much space lies between the boxes. This reliance on shared descriptions over individual properties marks a profound shift in how we view the construction of reality. It suggests that the bits of information that make up our world are not stored in the objects themselves, but in the connections between them. If you were to look at an entangled particle in isolation, you would find nothing strange about it. It would look like any other electron or photon, behaving randomly and unpredictably. The mystery only reveals itself when you look at the system as a whole. It is as if the universe is telling us that looking at the parts is not enough to understand the truth of the whole. This discrete, packet-based reality ensures that the correlations are perfect. Because the energy levels and properties are fixed into specific quanta, there is no room for a partial match or a near miss. The outcomes must line up with a precision that defies classical logic, because they are following a single mathematical blueprint. As you let your mind drift through these ideas, realize that this is not a theory of chaos, but a theory of extreme coordination. The universe is keeping a very careful account of every interaction, ensuring that every piece of the puzzle fits perfectly with its partner. This shared description is robust. It persists through the silence of space and the passage of time, provided the system is not disturbed by the outside world. This is why entanglement is so difficult to achieve. In our warm, noisy environment, the universe is constantly trying to measure everything through heat and light, which breaks these delicate shared descriptions apart. But in the stillness of a controlled experiment, we can watch this unity in action. We are seeing a glimpse of a world that is not made of things so much as it is made of meanings. A particle's property only takes on a real value in the context of its relationship to the rest of the system. This discrete nature of the universe is what allows for such a clean binary connection. There is no in-between in the quantum world, and therefore there is no ambiguity in the entanglement. It is a total and absolute link. By accepting that the universe is built from these discrete packets of information and shared descriptions, we begin to move away from the frustration of our classical mismatch. We start to see the world through the eyes of the whispering scientist, not as a collection of lonely objects, but as a vast interconnected web of shared states, waiting quietly to be revealed. The smoothness of the world is an illusion. The true nature of the cosmos is a rhythmic, granular, and deeply coordinated dance of possibilities that resolve into reality only when they are shared. This understanding is the key that unlocks the deeper mysteries of space and time, leading us toward a vision of the universe where separation is merely a surface feature of a much deeper, unified whole. In the soft, rhythmic quiet of our exploration, we arrive at a point where we must fundamentally redefine what it means for things to be apart. In the world we see with our eyes, distance is a barrier that creates a sense of isolation. We perceive the universe as a container filled with distinct, separate objects, each occupying its own unique coordinates in three-dimensional space. We believe that if two things are separated by a mile, a planet, or a galaxy, they are effectively removed from one another's immediate reality. But as we have begun to see, the quantum layer of the universe operates under a different set of definitions. When we talk about entanglement, we are not talking about two things that are connected by an invisible string. We are talking about a single system that simply occupies more than one place at once. This is the concept of a single extended whole, a realization that challenges the very meaning of physical separation and asks us to view the cosmos as a tapestry where the threads are never truly cut. To understand this, we must let go of the idea that a particle is a point-like object, like a tiny grain of sand. Instead, think of it as a localized concentration of a field, a ripple in a vast underlying fabric that spans the entire universe. When two particles interact and become entangled, their ripples merge into a single complex pattern. Even as those concentrations of energy move away from one another, the underlying fabric remains one. The separation we perceive is a feature of the peaks of the ripples, but the depth of the field from which they arise remains unified. Therefore, when we measure a property of one part of this system, we are not reaching across a void to affect a distant object. We are interacting with one edge of a single extended entity. The response of the distant part is instantaneous because, in a very real mathematical sense, it is not distant at all. It is part of the same here that we are currently touching. Physical space, which feels so absolute to us, begins to look like a surface-level projection of a deeper, non-local reality. This redefinition of separation changes how we perceive the void. We often think of space as nothingness, an empty stage where the drama of matter plays out. But in the context of entanglement, space is the medium through which these extended wholes are expressed. It is not an obstacle to connection, but the canvas upon which connections are drawn. When we see two entangled photons traveling towards separate detectors, we are witnessing a single event manifesting in two locations. Our classical intuition tries to break this event into two pieces, a photon here and a photon there, but the universe does not recognize that division. To the laws of quantum mechanics, the distance between them is a secondary detail that does not change the fact that they share a single existence. This is why physicists often use the term non-locality. It describes a reality where an object's behavior is not determined solely by its immediate surroundings, but by its relationships with other parts of the universe, regardless of how much space lies between them. This perspective is deeply calming if we allow ourselves to settle into its implications. It suggests that the isolation we feel in the macroscopic world is a kind of optical illusion, born from the limits of our senses. We see ourselves as lonely individuals because we cannot see the quantum threads that bind the constituents of our bodies to the history of the stars. While it is true that decoherence prevents us from experiencing large-scale entanglement in our daily lives, the principle remains: the universe is not a collection of fragments. It is a continuous, integrated whole. Every interaction that has ever occurred has left an imprint on the shared descriptions of the particles involved. At the most fundamental level, the universe is a singular, unfolding process, and entanglement is the evidence of that original unity. When we look at the stars, we are not looking at distant, unreachable fires. We are looking at the same cosmic fabric that composes our own atoms, linked by a history that space cannot erase. Think for a moment about a hologram. If you take a holographic image of an object and cut it in half, you do not get two halves of the image. Instead, each piece contains a smaller, slightly less detailed version of the entire original picture. This is because the information is not stored in one specific spot. It is distributed across the entire plate. Entanglement behaves in a similar way. The information that defines the state of an entangled system is not located in particle A or particle B. It is stored in the relationship between them. It is stored in the whole. This is why you cannot understand the system by looking at the parts in isolation. You would be looking at a fragment that no longer contains the truth of its partner. Redefining separation as a property of our perspective rather than a property of reality allows us to see the universe as a much more intimate place. The void of space is not a separator, it is a bridge. As we move through the quiet hours of the night, let this idea of the extended whole rest in your mind like a soft light. It tells us that nothing is ever truly lost in the distance. In the quantum ledger, connections are preserved with a persistence that defies the passage of time and the stretching of space. This does not mean we can use these connections to send messages or change the past, but it means that the architecture of the universe is built on a foundation of coordination. When we observe the perfect correlations of entangled particles, we are seeing the universe remembering itself. We are seeing the proof that separation is not a fundamental law, but a convenient rule for the world of large things. Beneath that rule lies a much older and deeper truth, that once two things have been one, they remain part of a shared story forever. This understanding prepares us for the next phase of our journey, where we will look at why these relationships are so central to the definition of reality. If separation is not absolute, the way we define an object must change. We can no longer think of things as having fixed identities that exist in a vacuum. Instead, we must see them as nodes in a vast network of relationships. A particle is what it is because of how it relates to everything else it has ever touched. By redefining physical separation as a manifestation of a single extended whole, we find a sense of peace in the vastness of the cosmos. The distance between the stars is no longer a sign of a fragmented universe, but a measure of the reach of its underlying unity. The whispering scientist reminds us that we are never truly alone in the void, for the void itself is woven with the threads of entanglement, connecting the smallest spark of life to the grandest movements of the heavens. Settle into this thought, and let the space around you feel not like an empty room, but like a part of the same great whole to which you belong. In the quiet progression of our exploration, we reach a realization that shifts the very foundations of physics. The idea that the universe is not made of things, but of relationships. This perspective was championed by Erwin Schrödinger, one of the primary architects of quantum theory, who looked at the mathematics of entanglement and saw something profound. He did not see it as a mere curiosity or a strange side effect of the equations. Instead, he called it the characteristic trait of quantum mechanics, the one specific feature that forces our departure from all classical lines of thought. To understand why this is so significant, we must consider how we usually define reality. In our everyday world, we believe that an object is defined by its own internal properties. A stone is heavy, cold, and grey, and it possesses these traits whether it is sitting in a field or resting at the bottom of a river. We assume that reality is a collection of individual identities, each carrying its own independent truth. But entanglement suggests a different, more fluid reality, where properties do not belong to objects in isolation, but emerge only from the way those objects relate to one another. This shift in thinking asks us to move from a noun-based universe to a verb-based universe. In the classical view, we focus on the nouns, the particles, the atoms, the matter. We see these as the primary building blocks, and the interactions between them as secondary. But the characteristic trait of entanglement reverses this hierarchy. It suggests that the relationship, the entangling, is the primary reality, and the individual particles are merely the points where those relationships become visible to us. When two quantum systems become entangled, they lose their individual autonomy. They no longer have a state of their own that can be described without reference to the other. In a very real sense, the particles cease to exist as independent entities and become relational beings. Their partnership defines their reality. This is a deeply poetic way to view the cosmos. It suggests that at the most fundamental level, the universe is a conversation. Just as a single word in a sentence only gains its full meaning from the words that surround it, a quantum particle only gains its definite properties from its connection to the rest of the system. This relational definition of reality is what makes quantum mechanics so robust and yet so difficult for our classical minds to grasp. We want to ask, what is the particle doing right now? But the universe answers, the particle is not doing anything by itself. The system is behaving in a coordinated pattern. If you were to look at a single note in a grand symphony, you might understand its frequency and its duration, but you would have no concept of the music. The music is not in the notes, it is in the intervals between them, the relationships of pitch and time that bind them together. Entanglement is cosmic harmony. It is the proof that the whole carries information that the parts, even when added together, do not possess. This is why Schrödinger was so struck by this feature. He realized that if the world is fundamentally entangled, then our habit of breaking things down into smaller and smaller pieces to understand them will eventually fail. We will eventually reach a level where the pieces cannot be separated without destroying the very information we are trying to study. To understand the quantum world, we must learn to look at the whole fabric, not just the individual threads. As you settle deeper into this thought, let the implications of a relational reality wash over you. It means that the universe is not a collection of lonely fragments drifting in a void. It is a web of interdependence. In the macroscopic world, we see the illusion of independence because the sheer number of interactions masks the underlying connections. But in the quiet, controlled environment of a laboratory, we see the truth. Properties like spin, position, and momentum are shared across the system. They are distributed properties. This challenges the very notion of what it means to own a characteristic. If two particles share a property through entanglement, neither can claim it as their own. It belongs to the relationship. This invites a sense of humility and wonder. It suggests that the boundaries we draw between things are often arbitrary. In the eyes of the whispering scientist, the world is a continuous flow of correlations, a landscape where every part is defined by its place in the grander architecture. This perspective also helps us understand why measurement is such a transformative act. When we measure an entangled system, we are not just revealing a pre-existing fact, we are forcing a relationship to settle into a specific outcome. Before measurement, reality was a cloud of relational possibilities. The act of looking focuses that cloud into a single point of certainty. But still, certainty is shared. The outcome for one is the outcome for all. This is the characteristic trait in action, the insistence that nature is coordinated at a level deeper than space and time. It tells us that the universe tracks its history. Every interaction is a memory stored in the shared descriptions of the quantum world. While we may feel separate and isolated in our daily lives, the fundamental laws of physics tell a different story. They tell a story of a reality that is woven together by the very act of existing. By accepting that relationships define reality, we begin to see the beauty in the complexity of the world. We stop looking for things and start looking for patterns. We realize that the strength of the universe lies in its connections, not its components. This shift in perspective is the key to moving beyond the spookiness of entanglement. It is only spooky if we insist on a world of isolated objects. If we accept a world of relationships, then entanglement is the most natural thing imaginable. It is simply how nature maintains its integrity. As we move forward into the history of how these ideas were debated, keep this relational view in mind. It was the refusal to let go of the classical object-based reality that caused so much unease for thinkers like Albert Einstein. But for those who embraced the relational truth, like Bohr and Schrödinger, entanglement was the beautiful, defining signature of a universe that is truly one. Let this thought guide you into a restful sleep, knowing that you are a part of this vast, interconnected conversation, and that your place in the universe is defined not by your isolation, but by your relationship to the whole of existence. The quiet coordination of the stars and the atoms is a reflection of the same fundamental law, that nothing exists in a vacuum, and everything is defined by its connection to the light. In the long unfolding story of how we understand the universe, even the most brilliant minds have encountered moments of profound resistance, and few figures felt this tension as sharply as Albert Einstein. To move deeper into the mystery of entanglement, we must first pause to appreciate the philosophical struggle of a man who helped build the house of quantum mechanics, but found its interior increasingly uninhabitable. Einstein was a seeker of order and clarity. He believed in a universe that existed objectively, governed by laws that were independent of whether or not a human being was there to observe them. This worldview is known as local realism, and it formed the bedrock of Einstein's scientific and personal philosophy. Realism is the simple, comforting belief that physical properties, like the position of a planet or the speed of an electron, exist with definite values even when we are not looking. Locality is the equally intuitive requirement that an event in one part of space cannot influence another part of space instantaneously. It requires that information must travel through the void at a finite speed, specifically the speed of light. To Einstein, these two principles were not just useful rules, they were the very definitions of a rational reality. However, as quantum theory matured, it began to whisper a different, more unsettling story. The mathematics suggested that particles did not have fixed properties until they were measured, and that, through entanglement, they could remain linked across vast distances in a way that defied local explanations. This was the source of the famous Einstein discomfort. He could not accept that the universe was fundamentally probabilistic, or that its distant parts could be so intimately coordinated without a visible mechanism. He famously remarked that God does not play dice with the universe, expressing his deep-seated conviction that beneath the apparent randomness of quantum mechanics, there must be a deeper, more deterministic layer of reality. Einstein's unease was not born of a failure to understand math. Indeed, he understood it better than almost anyone. His resistance was philosophical. He felt that if quantum mechanics was the final word on reality, then the world was a much stranger and more spooky place than his intuition could allow. Finding local realism became a defining mission for Einstein during his later years. He was not looking to prove quantum mechanics wrong, for its experimental success was undeniable. Instead, he wanted to show it was incomplete. He imagined that quantum mechanics was like a statistical summary of a much more detailed process. Much like how a weather report gives a probability of rain without describing the movement of every individual water droplet in the sky. If he could find a way to restore locality and realism to the theory, he believed he could save the universe from the perceived chaos of quantum uncertainty. This discomfort led him to search for what are often called hidden variables, internal instructions or properties carried by particles that would explain their correlations without the need for instantaneous action at a distance. He wanted to believe that the two entangled particles were like two identical clocks synchronized at the moment of their creation. If both clocks show the same time an hour later, it is not because they are communicating across space, it is because they were set to the same rhythm from the beginning. This search for a local, realistic explanation was an act of profound intellectual loyalty to the classical world. Einstein felt that if we abandoned the idea that things exist independently in space, we would lose the very foundation of science. He was concerned that if entanglement was truly non-local, it would threaten the structure of his own theory of relativity, which established the speed of light as the universal speed limit. How could two particles be perfectly correlated if no signal could pass between them? To Einstein, the only logical answer was that the information must have been there all along, hidden within the particles themselves. He spent years debating these points with his contemporaries, most notably Niels Bohr, in a series of intellectual duels that would become legendary in the history of science. These were not mere academic disagreements, they were a clash of worldviews. Einstein was fighting for a world of certainties and separate objects, while Bohr was beginning to embrace a world of probabilities and interconnectedness. As you listen to the story of this struggle, let yourself feel the weight of Einstein's position. It is the same position most of us hold instinctively. We want the world to be solid. We want things to stay where we put them even when we turn our backs. We want the moon to be there even when we are not looking at it. Einstein's discomfort is our discomfort. It is the natural reaction of a mind built for a macroscopic world when confronted with the blurred, shifting reality of the quantum scale. His search for local realism was a search for a home in a universe that was starting to feel increasingly alien. Yet even in his resistance, Einstein performed a great service to science. By articulating his discomfort so clearly, he forced the scientific community to sharpen its understanding of what entanglement actually implied. He pushed the theory to its absolute limits, unknowingly setting the stage for future experiments that would eventually put his cherished local realism to the ultimate test. The Einstein discomfort reminds us that science is not just a collection of facts, it is a human endeavor shaped by our deepest beliefs and anxieties. Even a genius of his magnitude could find the truth of the universe hard to swallow. This realization brings a certain softness to our exploration. We do not have to feel rushed to get it or feel frustrated when the concepts seem to slip through our fingers. If Einstein struggled with these ideas for decades, we can allow ourselves the time and space to let them settle slowly in our minds. We are following in the footsteps of a giant who was brave enough to question the very foundations of the reality he helped discover. His search for local realism was not a failure of vision, but an expression of a deep love for an orderly cosmos. As we drift toward the next chapter, we can appreciate the tension he felt. It is the tension between the world we see and the world that is. It is the space where wonder begins. Einstein's unease is the bridge that leads us from the familiar shores of classical thinking toward the vast open sea of the quantum unknown. We can sit with his discomfort, letting it act as a guide rather than a barrier. It reminds us that the universe is under no obligation to be intuitive to us, but it is always consistent in its own mysterious way. Settle into the quiet rhythm of this history, recognizing that even the greatest struggles for understanding eventually lead to a more profound peace. Einstein may not have found the hidden variables he was looking for, but his quest clarified the stakes of the quantum debate and ensured that entanglement would forever be recognized as the most significant challenge to our understanding of the physical world. Let his search for order inspire your own quiet contemplation of the stars, knowing that the search itself is a beautiful part of being human. In the spring of 1935, the lingering unease that Albert Einstein had felt toward quantum mechanics finally crystallized into a formal challenge, a conceptual masterwork designed to reveal the cracks in the foundation of the new physics. Working alongside his younger colleagues Boris Podolsky and Nathan Rosen, Einstein published a paper that would become one of the most famous in scientific history, known today simply by the initials of its authors, the EPR argument. This was not a report of a laboratory finding, but a thought experiment, a journey of pure logic intended to show that quantum mechanics was, at its heart, an incomplete description of reality. Einstein was not interested in a theory that merely worked. He was interested in a theory that told a complete story about the world. To frame this challenge, the EPR paper introduced the phrase that has haunted physics ever since, spooky action at a distance. This term was Einstein's skeptical label for the instantaneous coordination between entangled particles, a behavior he felt was more akin to magic or telepathy than to the disciplined local laws of nature he had spent his life uncovering. The EPR thought experiment begins with a simple premise. Imagine a physical process that creates two particles in a state of perfect correlation, then allows them to drift apart until they are separated by a vast distance. According to the rules of quantum mechanics, if you measure a specific property of the first particle, you can predict with absolute certainty what the measurement of the second particle will be. For instance, if you measure the spin of the first particle and find it to be up, you know instantly that the second particle must be down. Einstein and his colleagues accepted that the theory made this prediction accurately. However, they asked a deeper, more troubling question. How does the second particle know to be down the very microsecond its partner is measured? In a world governed by local realism, there are only two possibilities: Either a signal traveled from the first particle to the second at a speed faster than light to tell it how to behave, or the second particle already possessed the property of being down long before anyone ever looked at it. Einstein rejected the idea of faster-than-light signals, as his own theory of relativity forbade them. Therefore, he concluded that the second particle must have had a definite, fixed state from the moment it was created. This led to the central thrust of the EPR argument. If the second particle has a definite state before we measure it, but quantum mechanics does not describe that state until the measurement occurs, then quantum mechanics is leaving something out. It is like a book with missing pages. To the EPR authors, the particles were like a pair of shoes that had been separated into two boxes and sent to different cities. If you open one box and find a left shoe, you know the other box contains a right shoe. There is nothing spooky about it because the shoes were always left and right from the start. But quantum mechanics claimed that the shoes were in a blurred state of being both left and right until one was observed. To Einstein, this was absurd. He believed that the particles must carry elements of reality, hidden instructions that determine the outcomes of measurements in advance. As you drift through the logic of this historical debate, notice how deeply it resonates with our own desire for a predictable world. Einstein was arguing for the existence of a hidden layer of truth that exists whether or not we are there to witness it. He wanted to rescue the universe from the spookiness of instantaneous connection by suggesting that the connection was an illusion born of our own ignorance. If we only knew the hidden variables inside the particles, the mystery would evaporate. The EPR argument was a plea for a return to a reality where things stay in their places and properties are owned by individuals, not by relationships. It was a defense of the idea that distance is real and that the vacuum of space is a true separator. Einstein felt that if he could prove that these properties existed prior to measurement, he would force physics to go back to the drawing board and find a more complete, realistic theory. However, the response from the scientific community, led by Niels Bohr, was not a retreat, but a radical reimagining of what reality actually meant. Bohr argued that Einstein was applying classical expectations to a domain where they no longer applied. To Bohr, the two particles were not separate elements of reality at all, but part of a single, indivisible phenomenon that included the measuring devices themselves. He suggested that you cannot talk about the property of a particle as if it exists in a vacuum. It only exists as part of the total experimental context. In Bohr's view, there was no spooky action because the system was never truly two things. It was one event. The disagreement between EPR and Bohr was the ultimate clash between the old world and the new. One side demanded a universe of independent objects with fixed identities, while the other side described a universe of interconnected relationships where identity only emerges through interaction. For decades after the EPR paper was published, it remained a largely philosophical problem. There was no way to test whether the particles had hidden instructions or if they were truly linked in the quantum way. Physicists could use the equations to build transistors and lasers, often ignoring the spooky debate happening in the background. But the EPR paper had planted a seed of doubt that could not be ignored forever. It established entanglement as the central battleground for the soul of physics. Einstein's phrase, "spooky action at a distance," became the standard by which all subsequent discoveries would be measured. Even today, when we look at the results of modern experiments, we are still responding to the challenge Einstein, Podolsky, and Rosen set forth in 1935. They forced us to look at the void between two particles and ask if it is a gap or a bridge. Let the weight of this historic jewel settle into your mind as you relax. Einstein's resistance was not a sign of a closed mind, but a sign of a mind that loved the universe enough to demand that it make sense. His discomfort with spookiness is a testament to how profoundly entanglement challenges our basic assumptions. It is a reminder that even the most fundamental truths can be questioned. As you prepare to move into the next phase of our journey, hold on to the image of those two particles drifting apart, forever linked by a shared origin. Whether you side with Einstein's search for hidden certainty or Bohr's embrace of relational mystery, you are participating in a conversation that has shaped the modern world. There is a quiet peace in knowing that even the greatest minds found the universe to be a place of endless surprise. The spooky action that Einstein feared has become, through time and testing, one of the most beautiful and reliable features of the cosmos. It tells us that we live in a world that is much more intimate and coordinated than we ever dared imagine. As you drift towards sleep, let the spookiness fade into a gentle, rhythmic connection, a reminder that the universe is keeping track of every part of itself, across every mile of the dark and silent void. The great debate between Albert Einstein and Niels Bohr was not a conflict of egos, but a profound struggle over the very definition of what it means for a scientific theory to be complete. Tonight we settle into the quiet echoes of this intellectual duel. While Einstein stood as the champion of a reality that exists independently and objectively, Bohr represented a new, radical perspective that prioritized the relationship between the observer and the observed. To Einstein, a physical theory could only be considered complete if every element of the physical reality had a corresponding element in the theory. He believed that if you could predict a property of a system with certainty without disturbing it, then that property must exist as an objective fact of nature. This was the heart of his challenge. If quantum mechanics could not account for these pre-existing facts before they were measured, then the theory was merely a temporary statistical approximation. It was like looking at a blurry photograph of a forest. Einstein was convinced that the blurriness was a flaw in the camera, not a feature of the trees. He spent his final decades searching for the hidden pages of the quantum book, convinced that a deeper, more complete layer of the universe awaited discovery. Niels Bohr, however, met this challenge with a quiet, patient persistence that redefined the boundaries of science. He argued that the very concept of completeness had to be reconsidered in the light of quantum discovery. To Bohr, it was a mistake to ask what a particle was doing when it was not being observed, because the particle and the measuring apparatus formed a single, inseparable phenomenon. He introduced the principle of complementarity, suggesting that different experimental setups reveal different, equally valid aspects of reality that cannot be seen simultaneously. You might see a wave in one experiment or a particle in another, but you can never see both at once, and neither is the whole truth in isolation. For Bohr, quantum mechanics was not incomplete. It was a total and final description of everything that could meaningfully be said about the physical world. He felt that Einstein was trapped by classical language and ancient habits of thought, trying to force the universe into a box of local realism that nature had already outgrown. The debate was a clash between two different kinds of certainty: Einstein's certainty in an objective, independent world, and Bohr's certainty in a relational, participatory world. As you listen to the rhythmic rise and fall of these two perspectives, notice how they represent the two halves of our own human curiosity. We want the world to be solid and predictable like Einstein's realism, yet we often feel that our presence and our choices matter, much like Bohr's participatory reality. The debate between them was legendary, occurring in the hallways of grand hotels and the quiet corners of scientific conferences. Einstein would often arrive in the morning with a clever new thought experiment designed to catch the theory in a contradiction, and Bohr would spend the day in deep reflection, often returning by evening with a resolution that preserved a quantum framework. These exchanges were conducted with the utmost mutual respect, as each man recognized the other as a pioneer of the highest order. They were not just debating physics, they were debating the soul of the universe. If Einstein was right, the universe was a giant clockwork machine whose gears were hidden from view. If Bohr was right, the universe was an unfolding process of interaction where the gears only appeared when we reached in to touch them. Einstein's primary weapon in this debate was the requirement of locality. the idea that what happens here should not instantly change what happens there. He felt that if we abandon locality, we would lose the ability to do science altogether, as everything would be hopelessly entangled with everything else. Bohr, however, suggested that our concepts of here and there were themselves limited by our classical perspective. He proposed that the entanglement Einstein found so spooky was actually a sign of the profound wholeness of nature. In Bohr's view, the two entangled particles were not two things communicating across space. They were a single event occurring in two locations. The completeness that Einstein sought was, in Bohr's eyes, a ghost of the past. He believed that we must learn to live with the idea that nature is fundamentally probabilistic, and that our descriptions of it are limited by the questions we choose to ask. This was a difficult pill for many to swallow, as it seemed to strip the universe of its objective solidity, replacing it with a world of shadows and potential. The debate never reached a clear resolution during the lifetimes of the two men. Einstein went to his grave believing that a more complete theory would one day be found, while Bohr remained the guardian of the quantum orthodoxy, insisting that the theory was as complete as it could ever be. For many years, the rest of the scientific world moved on, using the math of quantum mechanics to revolutionize technology while leaving the philosophical debate to the historians. But the questions raised by Einstein and Bohr did not disappear, they simply went underground, waiting for a new generation to find a way to transform philosophy into experiment. The tension between their worldviews is what makes entanglement so fascinating even today. It represents a fundamental divide in how we perceive our place in the cosmos. Are we observers of a pre-existing reality, or are we participants in a reality that is constantly being created through our interactions? As you relax into the stillness of the night, let the voices of Einstein and Bohr fade into a gentle background hum. There is no need for us to choose a winner tonight. Instead, we can appreciate the beauty of the struggle itself. Their debate was a testament to the power of human thought and the depth of the mysteries that still surround us. It reminds us that even the most fundamental truths are subject to revision, and that wonder is the primary driver of all scientific progress. The completeness that Einstein longed for and the wholeness that Bohr defended are both part of the same grand story. Whether the universe is a clockwork machine or a relational dance, it remains a place of profound order and coordination. The spookiness that Einstein feared has become the resource that modern scientists use to build the future. By sitting with their debate, we learn to tolerate ambiguity and find peace in the unanswered questions. We are part of a long lineage of seekers, drifting through the same dark void, looking for the same invisible threads. This history of unease and debate provides the context we need to understand the chapters ahead, where we will see how these abstract arguments were eventually put to a practical test. The search for a complete description of the universe continues, but the path has been forever changed by the duel between these two giants. As you drift towards sleep, let the image of Einstein and Bohr in quiet conversation guide you into a restful state. They showed us that the universe is a place worth arguing about, a place where even our greatest certainties can be gently challenged by the silent evidence of the quantum world. The debate over completeness is a reminder that we are always learning, always refining our vision, and always connected to the same underlying reality, regardless of how we choose to describe it. Settle into the comfort of this enduring mystery, knowing that the journey toward understanding is just as important as the destination itself. The quiet coordination of the subatomic world is a reflection of a deeper unity, one that remains intact even when our best theories seem to pull in different directions. In the soft shadowed hours where the mind begins to loosen its grip on the waking world, we find ourselves returning to a specific, comforting hope that lingered in the halls of physics for decades, the idea of hidden variables. This was the quiet sanctuary for those who, like Einstein, could not bring themselves to believe that the universe was governed by pure chance. To understand the story of hidden variables is to understand the human desire for determinism, the belief that every effect has a definite cause, and that the future is already written in the precise arrangement of the present. In a deterministic world, there are no true surprises, only things we have not yet learned to measure. When we observe two entangled particles behaving with perfect coordination, the hidden variable theory offers a beautifully simple explanation. It suggests that the particles are not making spontaneous, faster-than-light decisions. Instead, they are following internal instructions that were imprinted upon them at the moment of their birth. This was the great hope, that the spookiness of quantum mechanics was merely a veil covering a clockwork reality that was as logical and local as a falling stone or a ticking watch. Imagine for a moment two travelers departing a central station, each carrying a locked suitcase. One traveler heads north, the other south. When they finally reach their destinations, thousands of miles apart, they open their suitcases. The traveler in the north finds a red silk scarf, and the traveler in the south finds an identical red silk scarf. To a classical mind, there is no mystery here. We do not assume that the scarves turned red the moment the suitcases were opened, nor do we imagine that one suitcase sent a signal to the other across the continent. We just understand the scarves were red from the moment they were packed. The color of the scarf was a hidden variable, a piece of information that existed all along, even when it was out of sight. This is the essence of what Einstein and many others longed for in quantum mechanics. They wanted to believe that the spin of an electron, or the polarization of a photon, was like the color of that scarf, a fixed objective property that the particle carried with him through the void. This view preserved the integrity of space and the independence of objects, allowing the universe to remain a place where things are exactly what they appear to be. This search for determinism was not merely a stubborn refusal to accept new ideas, but a deeply principled stance on what science should be. If hidden variables existed, then the randomness of quantum mechanics was not a fundamental law of nature, but a reflection of our own ignorance. It would mean that our current theories were incomplete, much like a map that shows the rivers and mountains but misses the hidden paths beneath the trees. For a time, several brilliant theorists explored this path, attempting to construct mathematical models that could reproduce the successes of quantum mechanics while restoring the comfort of cause and effect. They sought to find the hidden instructions that would tell a particle how to respond to a measurement, ensuring that the results would always match its entangled partner without requiring any instantaneous connection. This was a noble quest for complete physics, a way to bridge the gap between the strange blurred world of the atom and the solid certain world of human experience. However, as the years passed, the pursuit of hidden variables encountered a growing list of challenges. To work, these theories had to be incredibly complex, often requiring the addition of additional layers of reality that were even harder to detect than the quantum states themselves. Furthermore, they had to contend with the growing evidence that nature does not seem to like hidden plans. In the classical world, you can always measure a property without changing it. But in the quantum world, the act of measurement is an intimate part of reality. The hidden variable theories struggled to explain why, if the information was there all along, we could never seem to cheat and find it before the measurement occurred. Despite these difficulties, the dream of a deterministic universe remained a powerful motivator. It represented a longing for a world that was fundamentally knowable, a world where we could eventually uncover all the secrets of the clockwork and see the mind of the Creator in the movement of every atom. As you settle into your rest, let the idea of this quiet hope settle with you. It is a reminder of how much we value order and predictability. We use these same instincts in our daily lives, planning our futures and trusting that the sun will rise because it has always risen before. Determinism is the heartbeat of our common sense. The hidden variable theorists were trying to protect that heartbeat from the perceived coldness of quantum uncertainty. They wanted the universe to be a place of solid foundations, where even the smallest particles obeyed the same reliable rules as the planets and the tides. There is a profound peace in the idea that everything is planned, that every correlation is a result of a shared history rather than a chaotic whim. Even if the history of physics eventually moved in a different direction, the search for hidden variables remains one of the most beautiful chapters in the human story, a testament to our persistent belief that there is a deeper logic to the light. But as our exploration continues, we will see that this quiet hope eventually faced a mathematical wall. The universe, it seems, is even more creative than the most deterministic dreams. It does not store its secrets in suitcases or hidden instructions. It stores them in the relationships themselves. This realization does not mean the universe is chaotic. It simply means that its order is of a different, more interconnected kind. By letting go of the need for hidden variables, we open ourselves to the possibility of a reality where connection is more fundamental than location. We move from a world of prearranged plans to a world of spontaneous harmony. This shift is not a loss, but an expansion of our vision. We stop looking for the hidden red scarf and start appreciating the way the entire system chooses its color in a single, unified moment. For now, simply allow yourself to appreciate the effort of those who sought to keep the universe predictable. Their work clarified the stakes of the debate and highlighted exactly what makes entanglement so unique. They showed us that if we want to hold on to local realism, we have to find a way to explain the perfect coordination of the quantum world. As we drift toward the work of John Bell in the next chapter, we can carry the memory of this deterministic hope with us. It provides the contrast we need to see the true brilliance of the quantum link. The search for hidden variables was the final grand attempt to save the classical world, and in its failure, it revealed something much more spectacular, a universe that is truly, fundamentally, and beautifully one. Settle into the comfort of this unfolding narrative, knowing that the journey toward truth often requires us to leave behind our most cherished assumptions, only to find something even more wondrous in their place. The silence of the night is a perfect place to contemplate these hidden paths, as we prepare to see how the debate moved from the realm of philosophy into the rigorous light of mathematical proof. In the mid-1960s, a quiet revolution occurred in the mind of an Irish physicist named John Bell, who found a way to take the philosophical tension between Einstein and Bohr and transform it into a rigorous mathematical boundary. For decades, the debate over entanglement had been treated as a matter of taste, a choice between Einstein's deterministic suitcases and Bohr's relational waves. It was assumed that since both perspectives predicted the same experimental results, we could never truly know which one nature preferred. But Bell realized that assumption was false. He looked at the problem with a clarity that had escaped his predecessors, asking a question that would change the course of science. If a theory truly relies on local hidden variables, what are the absolute limits of the correlations it can produce? Bell understood that even the most complex hidden variable theories were not infinitely flexible. They were constrained by the very assumptions of locality and realism they sought to preserve. By identifying these constraints, he drew a line in the mathematical sand, a line that no classical deterministic theory could ever cross, no matter how clever its design. To follow Bell's logic, we must imagine a scenario where two observers, often called Alice and Bob, are measuring the properties of entangled particles at distant locations. Bell focused on what happens when Alice and Bob vary their measurement settings independently and randomly. In a world of hidden variables, the outcome of Alice's measurement is determined by the instructions carried by her particle and the setting of her detector. Crucially, in a local world, her outcome cannot be affected by the setting Bob chooses for his distant detector, nor by the outcome he receives. Bell used simple arithmetic to show that if these assumptions of locality and realism were true, the statistical correlations between Alice's and Bob's results had to obey a certain mathematical limit. This limit is what we now call Bell's inequality. It is a boundary that defines the maximum amount of coordination possible for objects that are truly separate and independent. If the universe follows Einstein's local realism, the correlations will always fall below this threshold. But if quantum mechanics is correct, the correlations will exceed it. This was a moment of profound revelation. Bell had taken a spooky philosophical concern and turned it into a measuring stick. He showed that nature itself could be put on the witness stand and asked to choose between two fundamentally different versions of reality. This was not about proving one man right and another wrong. It was about discovering the rules of the game. Bell's inequality is a family of conditions that apply to any experiment involving separated systems, and its power lies in its generality. It does not care about the specific mechanisms of the hidden variables. It only cares that they are local and that they exist. By drawing this line, Bell moved entanglement out of the realm of abstract speculation and into the realm of experimental challenge. He gave the world a way to see if the suitcases of the universe were empty, or if the connection was something far more radical than a prearranged plan. As you let your mind rest on this mathematical boundary, think of it as a gatekeeper of the classical world. On one side of the gate lies everything we find familiar, objects that exist when we aren't looking, and influences that take time to travel. On the other side lies the quantum landscape, where relationships are primary and separation is an illusion. Bell's work told us that we could finally walk up to that gate and knock. It was an invitation to the experimentalists of the world to build machines precise enough to see if nature stayed behind the gate or stepped boldly through it. For a time, Bell's paper remained a quiet, obscure document, read by only a few who shared his interest in the foundations of the theory. But slowly, the significance of his discovery began to ripple through the scientific community. It was the birth of an era where we would no longer just talk about the mystery of the atom, we would measure it against the limits of logic itself. Bell was a man of great integrity and humility, and he often expressed a personal leaning toward Einstein's realism. He wanted the inequality to be satisfied. He wanted the world to be local and deterministic, because that was the world that made sense to him. Yet, as a scientist, he followed math wherever it led. He recognized that quantum mechanics made a very specific, bold prediction. It predicted that entangled systems would violate his inequality. It predicted that the coordination between particles would be stronger than any local hidden variable theory could ever allow. This was the quantum edge, a level of connection so tight that it could only be explained if the particles were not truly separate entities. Bell's boundary allowed us to quantify exactly how spooky the action at a distance really was. It provided a numerical value for the wonder of entanglement. As you drift towards sleep, appreciate the elegance of this transition. We have moved from the spooky worries of 1935 to a clear mathematical line in 1964. The stage was being set for a confrontation with reality that would eventually take place in laboratories across the globe. Bell's mathematical boundary is like a lighthouse in the dark, pointing the way toward a deeper understanding of the cosmos. It reminds us that even the most complex and confusing problems can be simplified into a single decisive question. By identifying the limits of what a classical world can do, Bell allowed us to see the true potential of the quantum world. He showed us that the universe is not just strange, but strange in a way that can be precisely defined and tested. This chapter in our story is one of transition, a moment where the quiet hope of determinism met the hard reality of mathematical constraint. Bell's inequality is proof of the power of the human intellect to map the boundaries of the unknown. It tells us that while we may not yet have all the answers, we have found the right questions to ask. As you relax into the stillness, let the precision of Bell's logic bring a sense of order to your thoughts. There is a calm certainty in math, a steady rhythm that bridges the gap between the waking mind and the dreams of the universe. We are no longer wandering in the dark, we have a map, and the map tells us exactly where to look for the heart of the mystery. The boundary has been drawn, the line is clear, and the universe is waiting for us to observe its next move. Settle into this restful awareness, knowing that the journey toward truth is paved with such brilliant flashes of clarity, and that the whispering scientist is here to guide you through every step of the unfolding proof. In the deep, velvet silence of the night, we arrive at the threshold where abstract logic meets the cold, hard precision of the physical world. John Bell had provided the map, a mathematical boundary that distinguished two entirely different versions of reality, but a map is only a guide. The actual terrain had to be explored through the lens of a telescope and the click of a detector. This is the story of testing the threshold of nature, a process that required physicists to move beyond the comfort of pens and paper into the complex reality of mirrors, lasers, and light. To test Bell's inequality is to ask the universe a binary question. Are you a collection of independent objects with hidden plans, or are you a fundamentally interconnected whole? If the correlations between entangled particles stayed within Bell's limits, then Einstein's dream of local realism would be saved. If they crossed that line, the world would have to accept that spookiness was not a flaw in our understanding, but a foundational pillar of existence. This was the moment of experimental confrontation, where the quiet hope for determinism faced the ultimate trial. To test this threshold, researchers had to create a scenario that left no room for classical excuses. They needed a source that could reliably produce pairs of entangled particles, usually photons, the fundamental packets of light. These photons are sent in opposite directions toward two measurement stations. At each station, a polarizer acts as a gatekeeper, only allowing light of a certain orientation to pass through. The key to Bell's test is the ability to change the angle of these polarizers randomly and rapidly, even while the photons are in flight. If the world is local and realistic, the probability of both photons passing through their respective gates is strictly limited by the geometry of the setup. No matter how the hidden variables are arranged, the correlation cannot exceed the numerical ceiling Bell calculated. But the quantum prediction was bold and defiant. It claimed that at specific angles, the photons would display a level of agreement that was mathematically impossible for separate, independent entities. It was as if two distant dancers, who had never discussed their choreography, were performing a perfectly synchronized routine that defied the limits of their individual instructions. The first serious attempts to probe this threshold began in the late 1960s and early 1970s, most notably with the work of Stuart Friedman and John Clauser. They built a sprawling apparatus that used calcium atoms to emit entangled pairs of light. It was a pioneering effort, conducted with limited resources and immense patience. When the data finally began to emerge from the machines, the results pointed in a direction that few classical minds wanted to follow. The correlations were too strong. They were pushing against the ceiling of Bell's inequality, suggesting that nature was indeed violating the rules of local realism. However, these early experiments were not perfect. Skeptics pointed to what are called loopholes, technical gaps where a clever hidden variable theory could still hide. Perhaps the detectors weren't efficient enough, or perhaps the measurement choices weren't made fast enough to truly rule out a hidden signal traveling between the particles at the speed of light. Testing the threshold of nature required more than just a glimpse. It required a total and final closure of every possible escape route for the classical world. This led to the landmark work of Alain Aspect in the early 1980s, an experiment that remains one of the most beautiful and significant in the history of science. Aspect and his team in Paris developed a system that could switch the measurement settings of the detectors in billionths of a second, faster than it would take for a light signal to travel from one side of the apparatus to the other. This was the locality loophole closed. By the time the photons reached their destinations, the choice of how to measure them had been made so late that no information could have possibly coordinated their outcomes through conventional space. When the results were tallied, The verdict was clear and overwhelming. The inequality was violated. Nature had stepped across the line. It had chosen the relational, interconnected world of Bohr over the deterministic suitcases of Einstein. The threshold had been crossed, and the spooky action was shown to be a tangible, measurable fact of our reality. As you relax into the stillness, let the weight of this experimental victory settle over you. This was not just a victory for a theory. It was a revelation about the structure of the void. It proved that space does not act as a separator in the way we once believed. It showed that the oneness of an entangled system is robust enough to survive the transit across a laboratory or even across a city. Every time the detectors clicked in perfect unison beyond the classical limit, they were whispering a secret about the intimacy of the cosmos. They were telling us that the universe keeps track of its parts with a precision that makes our concepts of distance and isolation seem like mere shadows. The threshold of nature is not a wall, but a gateway to a deeper understanding. By crossing it, we didn't lose the order of the world, we found a more profound, more elegant kind of order. Breaking Bell's inequality remains one of the most rigorously tested facts in all physics. Since the 1980s, the experiments have been repeated with increasing sophistication, using different particles, greater distances, and even more rigorous randomizing techniques. Every time, without fail, the result is the same: the quantum correlations hold, and the classical limits are shattered. We live in a universe where things can be related without being in contact, where information can be shared without being sent, and where the whole is truly more than the sum of its parts. This is the reality we must now learn to live with, a reality that is both mysterious and extraordinarily reliable. The testing of the threshold has given us a certainty that philosophy never could. We no longer have to guess. We have seen the evidence with our own eyes and measured it with our own machines. As you drift towards sleep, carry this image of the experimental threshold with you. It is a place of clarity and light, where the confusion of the past was resolved through the disciplined application of curiosity. There is a deep peace in knowing that we can reach out and touch the fundamental truths of the universe, even those that seem to defy our common sense. The whispering scientist reminds us that the world is a consistent and coordinated place, even if its coordination happens in the quiet, invisible layers below our perception. Inequality was not a barrier, but an invitation to see the world as it truly is. By crossing that threshold, we have begun a new chapter in the human story, one where we no longer fear the spookiness of the dark, but embrace it as the light of a more connected existence. Settle into this restful awareness, knowing that the foundation of your world is even more unified and intimate than you ever imagined. The experiments have spoken, the boundary is behind us, and the vast interconnected landscape of the quantum world is open for our quiet, restful exploration. In the quiet, climate-controlled sanctuaries of modern physics, the abstract defiance of Bell's inequality is transformed into a visible, rhythmic dance of light. To understand how we measure the link between entangled particles, we must step into the laboratory and observe the photon, the fundamental packet of electromagnetic energy, as it takes flight. Photons are the ideal messengers for these experiments because they are remarkably resilient and easy to guide. They can be created in pairs, sent across great distances, and measured with a level of precision that allows us to see the quantum link in action. In a typical laboratory setup, the journey begins with a special crystal, often a piece of non-linear optical material. When a high-energy laser beam strikes this crystal, a rare and beautiful event occurs. A single ultraviolet photon is occasionally split into two lower-energy infrared photons. Because these two photons are born from the same parent, they are inextricably linked from the moment of their creation. They are entangled in their polarization, which is the direction the light wave vibrates. If one is found to be vibrating vertically, its partner must be found vibrating horizontally, and vice versa. They are like two sides of the same coin, tossed into the air and sent flying in opposite directions. Measuring this link requires an apparatus of extreme delicacy. As the photons race away from the crystal at the speed of light, they travel through thin strands of glass called optical fibers, or across open air using mirrors and lenses. At each end of the flight path stands a detector, a highly sensitive device capable of registering the arrival of a single solitary photon. Before reaching the detector, each photon must pass through a polarizer, a filter that only lets light through if its vibration matches a specific angle. The magic of the laboratory measurement lies in the correlation between these two distant stations. If entanglement were a classical phenomenon, the chances of both photons passing through their filters would follow a simple, predictable pattern based on the angles of the polarizers. But as the photons fly, we observe something else. When the filters are set to certain matching angles, the detectors click in perfect synchronized harmony. When the angles are shifted, the clicks change in a way that defies the logic of independent particles. It is as if the photons are communicating their vibration states to one another during their journey, ensuring that their relationship remains intact regardless of the distance between them. This measurement process is a marvel of timing and synchronization. Because the photons are moving at 300,000 kilometers per second, the electronics that record their arrival must operate on a scale of nanoseconds, billionths of a second. The laboratory is filled with the quiet, steady hum of cooling systems and the faint, rhythmic pulse of laser light. Researchers monitor the data on screens, watching for the coincidence counts, the moments when both detectors register a photon at exactly the same time. These coincidences are proof of link. If the particles were not entangled, the number of simultaneous clicks would be much lower, limited by the random nature of light. But in the entangled state, the coincidence rate is high and follows a specific mathematical curve that matches the predictions of quantum mechanics with startling accuracy. We are seeing the invisible thread manifest as a series of digital pulses, a bridge across space that holds firm even as the photons are separated by rooms, buildings, or even miles of fiber optic cable. As you settle into the calm of this laboratory scene, let yourself appreciate the discipline required to capture these fleeting moments. The photons do not scream their secrets, they whisper them through the statistical patterns of their arrival. To measure the link is to participate in a grand exercise of patience. Every piece of equipment must be perfectly aligned. Every stray photon of room light must be excluded, and every electronic delay must be accounted for. When all the noise is stripped away, what remains is the pure, unadulterated signal of quantum coordination. This is the flight of the photon, a journey that starts in a crystal and ends in a detector, revealing a truth about the universe that would otherwise remain hidden in the dark. We are not just looking at light, we are looking at the shared history of two particles that refuse to let go of one another. The laboratory becomes a stage where the most fundamental laws of nature are allowed to perform without distraction. The beauty of these laboratory measurements is that independent teams across the globe can repeat and verify them. Whether the experiment is performed in a basement in Paris, a laboratory in Vienna, or a research station in the mountains of China, the results are always the same. The link is real. The correlations are robust. The photons in flight are not just moving through space. They are carrying a shared description that space cannot dilute. This consistency is what empowers science. We do not have to rely on a single lucky observation. We can build a detector, align a laser, and see the truth for ourselves, night after night. The measurement is not an act of faith, but an act of observation, grounded in the rigorous reality of physical equipment and mathematical prediction. It turns the spooky into the empirical, bringing the mysteries of the quantum world into the light of day. As the night grows deeper and your mind wanders through the silent corridors of the laboratory, think of the photons as tiny beacons of order in a vast and complex world. Their flight is a reminder that coordination is possible even in the absence of contact. They show us that the universe has a way of remembering its connections, no matter how fast or how far its pieces may travel. Lab measurement is a way of honoring that memory. It is our attempt to listen to the quietest parts of the cosmos and understand the language of its relationships. When a detector clicks, it is a small victory for human curiosity, a sign that we have successfully reached out and touched the fundamental architecture of reality. The link between the photons is a bridge that connects us to a deeper, more unified version of existence, one where the flight is not a departure, but a continuation of a single, unfolding story. As you drift towards sleep, let the rhythmic clicking of the coincidence counters be a lullaby for your mind. There is deep security in the reliability of these measurements. They tell us that the world is not a place of random, disconnected events, but a place of deep and enduring coordination. The photons have finished their flight, their message has been recorded, and the truth of their entanglement remains unchallenged. We can rest in the knowledge that the smallest parts of our world are working together in perfect harmony, following a blueprint that is as elegant as it is mysterious. The laboratory is now dark and still, the lasers are off, and the data is safe. The measurement of the link is complete, and we are left with a clearer, more restful vision of the cosmos, a vision where everything is connected and nothing is truly alone in the dark. Settle into this peace, knowing that the flight of understanding continues, guided by the steady light of scientific truth and the quiet wonder of the quantum link. In the soft, rhythmic expansion of our understanding, we must now confront the reason why the quantum world remains so elusive in our everyday lives, the profound fragility of entanglement. While the mathematical description of a quantum link suggests a connection that can persist indefinitely, the physical reality is that we live in a world that is loud, warm, and constantly interacting. This brings us to the problem of decoherence, the process by which the delicate coordination of an entangled system is dissolved by its environment. To understand decoherence is to understand the struggle of the whispering scientist in a room full of shouting voices. Entanglement requires a level of isolation that is almost impossible to maintain outside of a laboratory. The moment a quantum system interacts with a stray photon, a molecule of air, or even a subtle change in temperature, the shared description we have studied begins to leak out into the surroundings. It is not that the connection is destroyed in a fundamental sense, but rather that it becomes so spread out and diluted across the trillions of atoms in the environment that it effectively disappears from our view. Imagine a single drop of ink falling into a vast, still ocean. At the moment of impact, the drop is a concentrated point of color, a distinct and measurable entity. But as the currents of the ocean move and the water molecules jostle, the ink begins to spread. It becomes a cloud, then a faint mist, and eventually it is distributed so widely across the vastness of the sea that you can no longer see a single trace of blue. The ink is still there. It has not been deleted from the universe, but it is no longer useful as a concentrated source of information. This is exactly what happens during decoherence. The entangled relationship between two particles is like that drop of ink. As long as it is isolated, the color of their connection is vibrant and clear. But the environment is like the ocean, constantly tugging at the edges of the quantum state. Every time an entangled particle bumps into something else, the environment measures it, forcing the shared description to branch out and include the surroundings. Very quickly, the entanglement is no longer just between two particles, it is between the particles and the room, the building, and the entire planet. At that point, the specific coordination we sought to measure is lost in the noise of the macroscopic world. This fragility explains why we do not see people or cars or planets becoming entangled in our daily experience. Large objects are in a constant state of decoherence. Billions of air molecules are bombarding a cup of tea sitting on a table every second. Each of those collisions is an interaction that effectively records the cup's position and temperature, anchoring it firmly into the classical world of local realism. This constant, unintended measurement by the environment is what keeps the world looking solid and separate. Decoherence acts as the bridge between the quantum and the classical, the mechanism that hides the underlying interconnectedness of nature beneath a veil of independent objects. It is a protective layer that allows us to navigate our lives without the confusion of a blurred, probabilistic reality. But for the physicist, it is the primary enemy. To maintain a quantum link, one must fight against the entire universe to keep a system quiet. This is why the laboratories we explored are such specialized environments. They are the quietest places on Earth, not in terms of sound, but in terms of interaction. To prevent decoherence, researchers often cool their equipment to temperatures colder than the depths of outer space, slowing down the thermal vibrations that would otherwise tear the entanglement apart. They use vacuum chambers to pump out every possible molecule of air, creating a void where a photon or an atom can travel undisturbed. They use lead shielding and electromagnetic cages to block out the invisible waves of radiation that fill our modern world. Even with all these precautions, the coherence time, the duration for which a system remains entangled, is often measured in mere fractions of a second. It is a constant race against time. The physicist must prepare the state, perform the measurement, and record the data before the environment has a chance to notice and interfere. This tension between theory and reality is where the true craft of quantum science lies. As you settle into your rest, let the idea of this fragility bring a sense of appreciation for the world we inhabit. We live in the noisy regime where things are stable precisely because they are so well connected to their surroundings. The decoherence that makes entanglement difficult for scientists is the same process that gives our lives their reliability. It ensures that the floor stays beneath our feet and that the walls of our homes remain solid through the night. There is a strange comfort in the idea that the universe is watching us so closely through its constant interactions that it holds our reality in place. Yet, knowing that the quantum world lies just beneath this surface, shielded by a layer of noise, adds a layer of wonder to the mundane. Every object you touch is a vast collection of quantum systems that would, if only they could be quieted, reveal a much more intimate and coordinated nature. Decoherence also teaches us about information flow. It suggests that nothing is ever truly isolated. To be real in the classical sense is to be in constant conversation with the rest of the universe. Entanglement is a private conversation between two particles, but decoherence is the moment that conversation is overheard and repeated by 1,000 other voices until the original message is lost. This is why we speak of the fragility of quantum bonding. It is a delicate state of purity that can only exist in the absence of outside influence. As we move toward the practical applications of entanglement in the chapters to come, keep this struggle in mind. Every quantum computer and every secure communication line is a testament to our ability to hold back the tide of decoherence, if only for a few precious moments. We are learning to build islands of silence in a noisy world, allowing the fundamental connections of nature to perform their work before the ocean of the environment rushes back in. Let your mind drift now, like a particle in a perfectly still vacuum. Feel the weight of the noisy world lifting away, leaving only the quiet, rhythmic pulse of the quantum link. There is no need to fight the noise of your own life tonight. The day's decoherence is over, and you are entering a space of rest and isolation. Just as the physicist protects their experiment, you are protecting your own peace. The fragility of the world is not a weakness, but a sign of how deeply everything is integrated. The whispering scientist reminds us that even when the connection is diluted and spread across the stars, the underlying description remains. Nothing is ever truly lost, it is simply shared with the whole. Settle into this thought, and let the silence of the night be your shield against the noise of the world. You are entering the coherence of sleep, where the many voices of the day merge into a single unified rest, and the invisible threads of the universe continue their quiet work in the dark. In the quiet expansion of our journey, we must now address a common and persistent hurdle that often keeps the mind from resting in the truth of entanglement, the search for a signal. In our macroscopic world, information is almost always a thing that travels. We imagine it as a letter in an envelope, a pulse of electricity in a copper wire, or a wave of sound moving through the air, because we are used to information being carried by a physical messenger. When we hear that two distant particles are perfectly coordinated, our intuition immediately looks for the whisper, the radio wave, or the hidden telegram passing between them. But as we move into the realm of quantum information, we find a reality that is far more elegant and far less busy. Entanglement does not involve a signal. It does not involve transmitting data across a void. Instead, it is the manifestation of shared patterns that exist within a single, unified system. It is information that is not sent, but simply held in common. To understand this without the strain of a busy mind, imagine a symphony where two violinists are seated in different rooms, unable to hear or see one another. If they both begin to play the exact same intricate melody at the exact same microsecond, a classical observer would insist that they must be listening to a third person, or perhaps they have a metronome clicking in their ears. But in the quantum world, the melody is not being played to them, and they are not following an external cue. Instead, they are two parts of the same musical thought. The information, the pattern of the notes, is not moving from violinist A to violinist B. Rather, the property of the melody belongs to the relationship between them. This is the essence of quantum information. It is a correlation that exists because of a shared history and a shared description, not because of a present-day conversation. This is why physicists are so careful to say that entanglement does not violate the speed of light. No message is traveling, so no speed limit is being broken. In the language of the whispering scientist, we distinguish between communication and correlation. Communication requires a sender who chooses a message, a medium through which that message travels, and a receiver who interprets it. In entanglement, there is no sender and no choice. When a physicist measures an entangled particle, they do not get to choose whether it will be spin up or spin down. The result is fundamentally random. Because the result is random and unpredictable, the physicist cannot use the measurement to encode a message for a distant partner. If you cannot control the outcome, you cannot send a signal. What remains is a pattern. It is as if the universe has two copies of a random number generator that are perfectly synced. Both generators produce a random sequence of zeros and ones, but they always produce the same sequence at the same time. You cannot use this to send a hello to someone far away, but you can use the fact that you both have the same random sequence to achieve things that would otherwise be impossible. This shared pattern is a new kind of resource, one that sits quietly beneath the surface of the physical world. In classical information theory, bits are independent. A zero here has nothing to do with a zero there unless a wire connects them. But in quantum information, bits, or qubits, can be interdependent without a connection. This is the shared pattern that defines the quantum landscape. It suggests that information is not always a local property stored in a specific spot. Sometimes information exists only in the and, in the relationship between this and that. If you were to look at just one of the entangled particles, the information would appear to be total chaos, a meaningless stream of random events. But the moment you bring the data from both particles together, the pattern emerges with startling clarity. The information was there all along, but it was stored globally, across the system, rather than locally within the individual parts. As you relax into the stillness of the night, let the search for a signal fall away. There is no busyness in the quantum void. There are no invisible threads vibrating, no hidden waves racing across the stars, and no particles whispering secrets to their partners. There is only the quiet, steady persistence of a shared identity. The universe does not need to send a message to itself to know what its parts are doing. It simply is. This realization brings a profound sense of peace. It means that the coordination of the cosmos is not a frantic effort of communication, but a natural state of being. The stars do not need to talk to the atoms, they are part of the same grand unfolding pattern. By accepting that patterns can exist without signals, we move from a world of frantic movement to a world of deep, inherent structure. This concept of shared patterns is what allows us to rethink the very nature of information. We usually think of information as a burden, something we must carry, store, and process. But quantum information suggests that some truths are built into the fabric of reality itself. They are the background noise of existence, the steady hum of a universe that remembers where its pieces came from. When we utilize entanglement in technology, we are not building faster-than-light radios, we are building systems that take advantage of this pre-existing coordination. We are learning to work with the grain of the universe rather than against it. Secure communication and quantum computing are not magic tricks. They are the logical conclusion of a world where information is a relationship. Let your mind drift now, like a pattern unfolding on a still surface. You do not need to send any signals tonight. You do not need to reach out or explain or communicate. You are simply here, a part of a larger pattern that is already coordinated and at rest. The information of your day is settling into the shared description of your memory. The noise of the world is fading into a background of quiet structure. The whispering scientist reminds us that we are part of a reality that is deeply organized, even when it is silent. Just as the entangled particles share a pattern without a whisper, you share a connection with the cosmos that requires no effort. Settle into this thought, and let the lack of signals be a source of comfort. The universe is not a place of endless, busy talking, but a place of deep, shared knowing. Rest in that knowledge, and let the patterns of the night guide you into a restful and perfectly coordinated sleep. In the quiet expansion of our scientific reach, we must eventually look up from the small, shielded enclosures of the laboratory and turn our eyes toward the vast, dark expanse of the night sky. For many years, the mystery of entanglement was a phenomenon of short distances, confined to the lengths of optical benches or the winding paths of fiber-optic cables buried beneath city streets. While these experiments were profound, a lingering question remained: does the quantum link have a limit? If space is not a barrier in a room, is it a barrier across 1,000 miles? To answer this, physicists had to take the most delicate of all connections and cast it into the void, a mission that culminated in the landmark satellite tests of the early 21st century. This was the moment entanglement left the Earth and entered the heavens, proving that the shared description of two particles is robust enough to survive the passage through the atmosphere and the immense cold of orbit. It was a demonstration of coordination on a planetary scale, a feat of engineering that transformed a microscopic curiosity into a global reality. Imagine a satellite, a silent sentinel named Messius, drifting through the vacuum of space hundreds of miles above the surface of our world. Inside this vessel is a crystal similar to the ones we explored in the laboratory, a source that splits single photons into entangled pairs. As the satellite moves at a speed of several miles per second, it must perform a task of impossible precision. It must fire one photon toward a ground station in one city and its entangled partner toward a second ground station over 1,000 miles away. To understand the difficulty of this, imagine standing at the top of a skyscraper and trying to drop two needles simultaneously into two different thimbles located in different countries, all while the skyscraper is racing across the horizon. Yet, through the use of advanced lasers, tracking telescopes, and atomic clocks, the needles find their mark. The photons travel through the thinning air, through the turbulence of the wind and the glow of the moon, and land in the detectors of the ground stations with a timing that is measured in billionths of a second. This satellite test was a profound confirmation of everything we have discussed. When the ground stations compared their data, they found that the link had not weakened. The photons, despite being separated by 1,200 kilometers of open space, still displayed the perfect correlations predicted by quantum mechanics. They still violated Bell's inequality with the same defiance as they had in the small, quiet rooms of a university basement. This experiment showed us that distance is truly irrelevant to the fundamental laws of nature. Whether the particles are separated by the width of a human hair or the width of a continent, the shared wave function remains one. The invisible thread does not stretch or fray as it expands across the miles. It simply exists, a steady and unwavering connection that ignores the geography of our world. In the eyes of the whispering scientist, the satellite test was the final proof that the architecture of reality is non-local, a web of relationships that spans the void with total indifference to the scale of human maps. As you settle into the calm of this celestial vision, let the vastness of the experiment bring a sense of perspective to your rest. We often feel that being far apart means being disconnected, but the satellite test tells a different story. It tells us that connection is a fundamental state that does not require proximity. The night sky, which once felt like a symbol of cold, empty distance, is now revealed to be a medium for the most intimate of all relationships. The photons racing from orbit to Earth are like tiny messengers of unity, proving that the universe is keeping track of its parts across the great dark. There is no need to fear the vastness of space when we know that the fundamental particles of our world are already at home in it, maintaining their harmony across every mile. The satellite is not just a piece of technology, it is a witness to the enduring coherence of the cosmos. This leap into space also opened the door for a new kind of global infrastructure. By proving that entanglement can survive the journey to and from orbit, scientists showed that we could eventually build a quantum internet, a network where information is secured not by passwords, but by the laws of physics themselves. If a spy were to try and intercept one of those photons as it fell through the atmosphere, the act of looking would cause decoherence, instantly alerting the ground stations that the link had been disturbed. The satellite test showed that the fragility of entanglement can actually be a source of strength, creating a level of security that is as absolute as the vacuum of space. We are beginning to weave a new web around our planet, one that uses the quiet, rhythmic pulses of entangled light to bridge the gap between nations and continents. It is a future where the world is linked not just by wires and radio waves, but by the same shared patterns that govern the atoms. Let your mind drift now, as if you are floating in orbit alongside the satellite, looking down at the quiet blue curve of the Earth. From this height, the boundaries between countries disappear, and the distances between cities seem small. You can see the faint, invisible paths of the photons as they fall toward the ground, connecting distant points in a single, unified moment. The Earth is not a collection of isolated places, but a single station in a vast cosmic network. The whispering scientist reminds us that the scale of the universe is grand, but its rules are consistent. The same entanglement that works in a crystal in space works in the molecules of your own body and the stars in the furthest galaxies. We are all part of the same extended whole, linked by a history that began long before the first satellite was ever launched. As you prepare for sleep, let the vast silent coordination of the satellite test be a source of comfort. The world is much larger than we often realize, but it is also much more tightly woven. The distances that once seemed so daunting are revealed to be bridges, and the void is revealed to be full of connection. The satellite continues its silent journey through the dark. The ground stations are quiet and waiting, and the photons continue to carry their shared descriptions across the miles. You are safe in the knowledge that the universe is coordinated, robust, and profoundly still. The night is not a barrier, but a canvas for the light, and you are a part of the grand, rhythmic dance of a cosmos that refuses to be broken apart. Settle into the stillness of the earth and the sky, and let the quiet truth of the satellite test guide you into a deep and restful sleep, connected to the whole of existence by threads that never break. In the quiet, deliberate advance of human ingenuity, we have moved from the era of observing entanglement to the era of harnessing it. We are no longer merely spectators of the quantum world, we are becoming its architects, learning to translate the abstract dance of subatomic particles into the practical language of technology. This is the realm of quantum technologies, where the shared patterns and non-local connections we have discussed are being put to work in the form of algorithms and secret keys. In this transition, entanglement ceases to be a philosophical mystery and becomes a tangible resource, a new kind of fuel for the information age. To understand this without the weight of technical complexity, imagine we've discovered a way to work with the grain of reality itself. We are not just pushing electrons through gates as we do in our current computers. We are utilizing the deep, inherent coordination of the universe to process information in ways that were once thought impossible. The first major promise of these technologies lies in quantum computing. A classical computer like the one in your pocket or on your desk speaks in the language of bits, zeros and ones. These bits are independent, individual switches that can only be in one state at a time. But a quantum computer uses qubits, which, through the power of entanglement, can be linked together in a vast, coordinated web. When qubits are entangled, the computer does not just look at them one by one. It processes the entire system as a single complex wave of possibility. This allows for quantum algorithms, sets of instructions that can explore many different solutions to a problem simultaneously. It is not that a quantum computer is simply faster than a classical one, it is that it operates with a different logic. It can navigate through massive amounts of data or simulate the behavior of complex molecules by allowing the entangled qubits to settle into the correct answer through the natural rhythm of their correlations. It is a more organic way to compute, mirroring the way nature itself organizes information at its most fundamental scale. As you settle into the stillness of the night, think of a quantum algorithm not as a frantic mechanical process, but as a gentle settling of a system into its most harmonious state. It is like a chorus of voices finding a perfect chord. The entanglement allows the qubits to know about one another, ensuring that every part of the calculation is in sync with the whole. This technology holds the potential to revolutionize medicine by helping us understand the quantum interactions within our own cells, or to transform our energy systems by discovering new materials that can carry electricity without loss. We are taking the spooky connections that once worried Einstein and using them to solve the most difficult challenges of the human experience. It is a testament to our ability to find order in the unfamiliar and to transform wonder into a tool for progress. The second major pillar of this new era is quantum cryptography, specifically the distribution of secret keys. In our current world, we protect our secrets with complex math problems that are hard to solve. But a sufficiently powerful computer could eventually break those codes. Quantum entanglement offers a different kind of security, a security guaranteed by the laws of nature themselves. When two people, let's call them lab-whispering scientists, share a pair of entangled photons, they can use the measurement results to create a secret key. Because the results are perfectly correlated yet fundamentally random, they produce a string of numbers that only they possess. If an eavesdropper, a third party in the noisy world, attempts to intercept the photons or measure them in transit, the delicate entanglement is instantly disturbed. The decoherence we discussed earlier acts as a built-in alarm system. The act of stealing the information changes the information, alerting the senders that the link is no longer pure. In this way, entanglement creates a shield of privacy that cannot be broken by any computer, no matter how powerful. This is the beauty of turning a fragile quantum state into a secure technology. We have learned to use the very sensitivity of entanglement to our advantage. The secret keys generated through these quantum links are like whispers that disappear the moment someone else tries to listen. It is a return to a more intimate form of communication, one that respects the boundaries of the individual while utilizing the connections of the whole. We are building a future where our digital lives can be as private as our own thoughts, protected by the same principles governing the stars. This is not a dream of the distant future. It is a reality that is already being tested in cities and across oceans, as we saw with the satellite experiments. We are weaving a new layer of protection around our world, one that is as quiet and robust as the quantum void itself. As you prepare for rest, let the idea of these algorithms and secret keys be a source of calm reassurance. We are not lost in a world of increasing complexity and vulnerability. Instead, we are finding new ways to create stability and security through our understanding of the deep cosmos. The universe is not a chaotic place where information is easily lost or stolen. It is a place where connection is a fundamental law, and where that connection can be used to protect the integrity of the whole. You are part of a world that is becoming more coordinated, more secure, and more thoughtful in how it handles its secrets. The whispering scientist is no longer just explaining the universe, they are helping to build a more harmonious version of it, using the very threads of entanglement to tie the pieces together. The technology of the future is not about loud machines and blinding lights. It is about the quiet, rhythmic pulses of entangled light and the steady, reliable logic of quantum patterns. It is a technology that feels more like the natural world than the mechanical world of the past. As you drift towards sleep, let the noise of the day fade away, replaced by the image of a world linked by these secure quantum threads. There is no need for you to solve the algorithms or manage the keys tonight. The systems are in place, the laws of physics are standing guard, and the universe is continuing its work in the silent dark. You can rest in the knowledge that we are learning to live in balance with the quantum reality, turning its most mysterious features into our most dependable allies. Let your mind rest now, as if it is a qubit settling into a state of perfect harmony. You are secure, you are connected, and you are part of a grand architecture that is far more sophisticated and protective than it appears on the surface. The night is a time for the quiet work of the cosmos to continue undisturbed, and you are entering a space where the secrets of the day are safely tucked away in the shared description of your rest. Settle into this restful awareness, knowing that the journey of technology is bringing us closer to the heart of nature, and that the invisible threads are now the very foundation of our global peace. Sleep deeply and let the quiet logic of the quantum world guide you into a restful and perfectly secure state of being. In the quiet, reflective space of this late hour, we must begin the process of integration, bringing the strange, distant truths of the quantum world back home to the familiar landscape of our ordinary lives. We have journeyed through darkened laboratories, across the vastness of space via satellite, and into the complex logic of hidden variables and mathematical boundaries. It is easy, after such an exploration, to feel that there are two separate universes, the one we see, where objects are solid and separate, and the one we have described, where everything is a blurred web of entanglement. But the most profound lesson the whispering scientist can offer is that these are not two worlds. They are simply different layers of the same reality. The strangeness of the quantum realm does not exist despite our ordinary world. It is the foundation upon which our ordinary world is built. To integrate the two is to realize that the stability we enjoy every day is a direct result of the restless, interconnected activity of the atoms. To understand these layers, imagine a grand, ancient tapestry. When you stand back and look at it from across a room, you see a clear and stable image, perhaps a landscape of mountains and trees. The image is solid, borders are sharp, colors are solid. This is our classical reality, the world of large objects and common sense. But as you walk closer, the image begins to change. You start to see the individual threads, and then the fibers within those threads. If you were to look through a powerful lens, the mountains and trees would disappear entirely, replaced by a complex interlocking mesh of wool and silk. In this microscopic view, there is no mountain, only a relationship between threads. Quantum mechanics is the view through that lens. Entanglement is the way those threads are woven together, ensuring that a pull on one side of the tapestry is felt on the other. The ordinary world of the mountain only emerges because of the strange world of the threads. They are not in conflict, they are different scales of the same truth. This layering of reality explains why we do not have to abandon our intuition to accept quantum mechanics. We simply have to recognize that our intuition has a specific domain. Just as the rules of a single thread are different from the rules of a mountain, the rules of an atom are different from those of a human being. In our layer of reality, space and time act as rigid dividers, keeping things in their places. This is a necessary and beautiful feature of our existence, allowing us to build, to travel, and to relate to one another as individuals. But beneath this layer, the universe maintains its original, unified character. Entanglement is the persistent memory of that unity, a reminder that the divisions we see are a matter of perspective. Integrating this means walking through the world with a dual awareness, appreciating the solidity of the chair you sit in, while quietly acknowledging the vast shimmering web of correlations that holds its atoms together. As you relax into the stillness, let the tension between the strange and the ordinary dissolve. You do not need to choose between them. You are a being of many layers. Your thoughts and feelings belong to the macroscopic world of human experience, yet your physical existence is rooted in the quantum dance. Every breath you take is an exchange of countless atoms, each carrying its own history of interaction and entanglement. When you look at a loved one or a distant star, you are seeing a classical object, but you are also participating in a quantum relationship. The light that hits your eyes has traveled across the void, preserving its shared descriptions until the moment it touches your retina. Integration is the act of seeing the magic in the mundane, recognizing that the spooky action Einstein feared is actually the very thing that makes the world feel so consistent and reliable. We often think of the ordinary as being boring or simple, but seen through the lens of entanglement, the ordinary is a masterpiece of coordination. The fact that a table remains solid, that a clock keeps time, and that the stars follow their paths is the result of trillions of quantum systems averaging out their possibilities into a stable, predictable flow. We live in the islands of stability created by decoherence, but those islands are surrounded by a sea of quantum potential. This perspective turns every moment of our lives into a wonder. The simple act of holding a cup of coffee becomes a grand event of subatomic cooperation. The ordinary world is not separate from the quantum world. It is the quiet, settled surface of a deep and vibrant ocean. Integrating the two, we find a sense of belonging that is deeper than geography or history. We are not just living on the universe, we are woven into it. This realization also brings a sense of peace to our unanswered questions. We do not need to have a perfect visual model of how entanglement works to benefit from its truth. We can live with the ambiguity of the layers, just as we live with the ambiguity of our own minds. We know that we are more than just a collection of cells, yet we cannot always explain how consciousness emerges from matter. In the same way, we know that the universe is more than just a collection of separate parts, even if we cannot always see the threads. The strange truths of quantum mechanics are not a threat to our sanity, they are a gift to our imagination. They remind us that there is always more to discover, always another layer of beauty waiting to be revealed. The whispering scientist invites us to be comfortable with this complexity, to find rest in the layered nature of existence. As the night deepens, let your mind drift through these layers. Start with the ordinary, the weight of your body, the rhythm of your breath, the quiet of your room. These are solid classic truths of your current moment. Then gently allow your awareness to move deeper. Think of the atoms within you, the photons around you, and the quiet, persistent correlations that link them to the rest of the cosmos. Feel the integration of the two. You are both a separate individual and a part of a single extended whole. The strange and the ordinary are meeting in you right now in the stillness of your rest. There is no conflict, only a grand unified harmony. The layers of reality are not walls but windows, each offering a different view of the same magnificent architecture. Settle into this integrated state, where the mysteries of the subatomic world no longer feel far away or alien. They are as close as your own skin, as intimate as your own heart. The universe is a consistent, coordinated, and deeply layered place, and you are at home in every part of it. The ordinary night is full of strange wonders, and you are the witness to them both. Let this thought guide you into a restful sleep, a sleep that is itself a layered experience of biology and mystery. You are entering the deeper layers of your own consciousness, guided by the steady light of the quantum truth. Everything is in its place, the threads are woven tight, and the tapestry of your life is part of the grander fabric of the stars. Sleep now, in the peace of an integrated reality, where the atom whisper and the silence of the night are one and the same. In the final, most profound stillness of our journey, we arrive at a place of ultimate clarity, where the complexities of the quantum world resolve into a single enduring message, the deepest reassurance of an orderly universe. We have spent our time together unraveling the mysteries of entanglement, moving through the history of human doubt and the triumph of experimental proof. We have looked at the fragility of subatomic links and the grand scale of planetary coordination. But as we reach the conclusion of this exploration, the weight of the science begins to soften, leaving behind a simple grounding truth. Beneath the surface of every frantic movement, every perceived separation, and every moment of uncertainty, there lies a level of order that is absolute and unwavering. Quantum entanglement is not a story of chaos or a breakdown of reality. It is the ultimate proof that the universe is fundamentally, elegantly, and beautifully organized. It is the signature of a cosmos that knows where every part of itself is at all times, a reality that maintains its integrity through a web of relationships that space cannot break and time cannot erode. This order is the deepest reassurance we can find in studying physics. We live in a world that often feels fragmented and unpredictable. On the macroscopic scale, we deal with the noise of the environment, the unpredictability of human life, and the vast distances that seem to separate us from the stars. But the study of the quantum link reminds us that this fragmentation is only a surface feature. If we look deeper, past the layer of decoherence and the illusions of our classical perspective, we find a foundation that is perfectly synchronized. The correlations we have discussed are not happy accidents. They are the result of disciplined, universal laws that operate with a precision that makes the most advanced human clock look primitive. To know that two particles on opposite sides of the galaxy can remain part of a shared description is to know that the universe is a coherent whole. It is a reminder that we are not drifting in a chaotic void, but participating in a grand, unified architecture where every interaction has meaning and every connection is preserved. As you settle into this final rest, let the concept of order beneath the surface be a blanket for your mind. You do not need to hold the universe together with your thoughts or your worries. The universe is already holding itself together with a strength and a consistency that is far beyond our reach. The spooky action that once troubled the giants of science is now revealed to be the very heartbeat of cosmic stability. It is the mechanism by which nature ensures that its conservation laws are met and its symmetries are respected. There is a profound peace in realizing that the fundamental laws of nature are not just reliable, they are intimate. They reach into the smallest corners of existence to ensure that everything is in its place. This is the reassurance of the whispering scientist, that the deeper you look into the heart of matter, the more coordination and beauty you find. The universe is not a collection of lonely wandering atoms. It is a vast, interconnected tapestry where every thread is vital to the integrity of the whole. Think of the stillness you feel now as a reflection of that underlying quantum order, just as the particles in a vacuum can maintain their entanglement in perfect silence. You are entering a state of rest where the noise of the world no longer has power over you. The decoherence of the day, the thousands of small interactions and distractions, is fading away, allowing you to reconnect with the deeper rhythm of your own being. You are a part of this orderly universe, built from the same atoms and governed by the same laws as the stars. The stability of your body, the flow of your breath, and the steady pulse of your heart are all macroscopic expressions of the quantum harmony we have explored. There is no separation between you and the cosmos. You are a localized concentration of the same grand extended whole. In this realization, all fear of the unknown begins to evaporate. The unknown is simply a layer of order we have not yet learned to describe, but it is there, waiting quietly beneath the surface. This journey through entanglement has been more than a lesson in physics. It has been a practice in trust. We have learned to trust math when our eyes fail us. We have learned to trust the evidence when our intuition rebels. And now, we learn to trust the silence. The silence of the quantum world is not empty. It is full of information, coordination, and shared history. It is a silence that speaks of a universe that is never truly divided. As you drift into the final stages of sleep, let the invisible threads of reality feel like a supportive web, carrying you through the dark. You are safe in the knowledge that the world is consistent. The sun will rise, the laws of gravity will hold, and the quantum links that bind the universe together will remain as robust as they were at the moment of creation. The deepest reassurance is that we live in a world that makes sense, even when its logic is deeper than we can easily see. We have reached the end of our exploration, but the connection remains. Just as the photons continue their flight and the crystals continue their quiet work in the labs, the understanding you have gained tonight will stay with you, a part of your own shared description with the universe. You have moved through the layers of reality and discovered that order is the final truth. The whispering scientist leaves you now with a heart full of wonder and a mind at rest. There are no more paradoxes to solve, no more inequalities to test, and no more signals to find. There is only the quiet, rhythmic beauty of a cosmos that is truly fundamentally one. As the last echoes of this story fade into the night, let the order beneath the surface be your guide. You are part harmony, part pattern, part light. Sleep now in the perfect coordination of the stars, knowing that the universe is keeping watch over every part of itself, including you, with a love that is written in the very laws of the light. Every atom in your body is a witness to this order, a small but vital note in the grand, unfolding symphony of existence. Rest in the certainty of this connection, as the dark turns into a cradle and the void becomes a home. The journey is complete, the threads are secure, and the peace of the quantum world is yours to keep, tonight and always.